So this is going to be a quick guide on a thermodynamics problem involving entropy and compressors. We have air entering a compressor steadily at ambient conditions 100 kPa, 22 degrees Celsius, and it leaves at 800 kPa. We have a Q out from the compressor of 120 kilojoules per kilogram and an entropy decrease of 0.4. So we're finding the exit temperature of the air, the work input to the compressor, and the entropy generation in all of this process. So we're going to start by finding T2, the temperature as the air exits the compressor. First, it's always good to write down what we have. We have T1 equals 22 degrees Celsius or 295 K. With entropy, most of the time you want to be dealing with degrees Kelvin. We have P1, 100 kPa. We have P2, 800 kPa. And then we have S2 is 0.6 of S1. We don't know exactly, we just know that it's a 40% decrease. So we're going to start with the formula for entropy of an ideal gas. So the delta S equals specific heat times ln T2 over T1 minus gas constant times ln P2 over P1. Going to rearrange this because we're solving for T2. So ln T2 over T1 equals the change in entropy plus the gas constant times ln P2 over P1, whole thing divided by specific heat. And then we have, so we can plug in our numbers, we get ln of T2 over 295 equals 0.4 plus 0.287 times ln of 800 over 100 kPa, which is just 8, whole thing divided by 1.005. So then, if we simplify this further, undo the natural log on both sides, we get T2 over 295 degrees Kelvin is equal to e to the 0.1958. So again, simplify that e and multiply by 295 degrees Kelvin, and we get a final temperature of 358.8 degrees Kelvin. So in the next part, we're finding the work into the compressor, and we know that work in is equal to the difference in enthalpy, or H2 minus H1, which is equal to specific heat times the difference in temperature, T2 minus T1, plus the heat leaving the system, Q out. So if we plug in our numbers, we get the work into the compressor equals 1.005 kilojoules per kilogram times 358.8 minus 295 in degrees Kelvin plus 120 kilojoules per kilogram. And then from that, we get a final answer of 184.122 kilojoules per kilogram. All right, now in the final part, part C, we're finding the change in entropy of the whole universe, so the system plus the surroundings. First, we need to find the change in entropy of the surroundings to do this, which is equal to Q out over temperature of the surroundings. So we have 120 kilojoules per kilogram for Q out, divided by 295 degrees Kelvin for temperature of the surroundings, which gives us an answer of 0.40678 kilojoules per kilogram Kelvin. So then the change in entropy in total is equal to the change in entropy of the system plus the change in entropy of the surroundings. So we have change in entropy of the system we already know, so we just need to plug it in. We get negative 0.4 kilojoules per kilogram Kelvin plus 0.40678 kilojoules per kilogram Kelvin, which gives us a final answer change in entropy of 0.00678 kilojoules per kilogram Kelvin.